8.1. I don't know if you ever heard of this before. Polar coordinates. Okay, so we're going to talk about what are polar coordinates and then why do we use them. Okay, so the first objective, plot points using polar coordinates. Then we're going to convert from polar to rectangular. Now, when you hear the word rectangular, you're talking about a regular XY point. Okay, and then go backwards, go from convert equations to polar and rectangular. So that's going to be our objectives for today. To start us off, I have a math shout out, mathematician. I try to incorporate a little bit of history, not as much as I can, but Isaac Newton. Let's talk about him. So he is generally credited with the development of polar coordinates. Okay. I mean, there's a lot of mathematicians that did some work with polar coordinates, but he's usually the one that says, hey, he's the guy that started it. And what's interesting is he published a book, and I'm probably going to butcher the name of it, but Method of Fluxons, I think is what it's called. And he offered 10 different types of coordinate systems. Instead of like an XY, we're going to do a different coordinate system here, but 10 different ones, just depending on the situation that you're working with. So that's pretty cool. But anyway, just thought I'd just give a little shout out to a math guy that kind of contributed to this lesson for today. So here's the question. So what are polar coordinates? It's a good question. So we take our normal XY system. We call that rectangular. You'll see why in a moment when we start drawing some things. And we change it to this. Instead of so instead of like a typical XY point, I'm going to locate this in a different way. I'm going to locate it by some radius from the origin, okay, so R being our radius, and then what angle it takes to get to that, okay? So my points are not going to be XY, my points are going to be R theta for that guy. And the origin, we call it the pole, okay? So XY plane, origin's just the origin, 0, 0. It's still 0, 0 at the pole, but still, that's what we're going to call our origin there. Okay, so we're just swapping out a coordinate system. So XY is gone, R theta is going to be put in its place. So what does that look like as a grid? Get ready to draw some circles. Okay, so here's a full-blown example. I'm going to try my best to draw this as symmetrically as possible. There we go. So that's 5 circles. Drawing 5 circles there. So the radius of the first circle is 1, radius of the second is 2, 3, 4, and 5. It's like a big target. Okay. And then what I'm going to do is draw angle measurements on here. And I'm going to use the angle measurements that we use on the unit circle. Okay, just to make it a little bit easier. So there's 30, 45, and 60. I'll go ahead and draw the other ones. Oh, it's that one. So there's second quadrant, third quadrant, full-blown polar coordinate grid. So again, if you look at these circles, so from here to here is a radius of 1. To the second circle will be a radius of 2, radius of 3, 4, and 5. Okay? I'm going to show you how to graph with it now. How do you plot points on this thing? It's actually pretty cool. So here we go. I'm going to write some facts about it, and as I'm writing facts about it, I'm going to, well, use a different color. Use pink. And I'm going to plot points using some of these facts. So if my radius is positive, then point P is located r units from the pole in the direction of theta. And I'll give you an example. So 2, 30 degrees. So if the radius, in this case this is my radius, if it's positive, and I'll explain what happens to the point when it becomes negative. If it's positive, then we're just going to go to that specific spot at 30 degrees. So here's what it looks like. So 30 degrees is here, okay? And on that line, I want to go where the radius is 2. Well, the radius is 2 right there. So there it is. I'll put there. Pink for a pink point there. So that's where that's located. Okay? Let's keep going. If r is negative, then point P is located r units from the pole in the direction of theta plus pi opposite of theta. So let me give you an example underneath there. And, what do you think, green? Use green for that one. Okay. So, I'm going to show you how to work with this. Again, go where 45 degrees is. Okay, so 45 degrees is here. So if it was a normal 3, you put the point there. But because it's negative, you're going to go in the entire opposite direction. You're going to go over here. Okay, I want to make sure I'm hitting the 3 mark. So right there is where negative 345 is. So if you have a negative radius, it's like a symmetry type of deal. You're going in the opposite direction. Okay, so that's what's going to be located. Now, the theta plus pi part, that's what it is. If I put the point here and have a negative radius, if I go pi radians, I get to this spot. Okay, so there's 2 ways of locating this. Either you can add pi to this to get to this point, or just know that I'm going directly across in the other direction. That's what that negative r value is going to do. Okay, I'm going to pause for a moment. Any questions on those 2? Does that make sense? Okay. If your radius is 0, then point P is located at the pole. I'll just put in parentheses, that's your origin. Okay? Now, the last 2 things I'm going to talk about is what if the angle's negative? Okay, what's that going to do? And we already have some experience with negative angles. We're just going to be going the other direction, right? That's what that's going to be. We're going to be going clockwise instead of counterclockwise. But let's write that down. So if theta is positive, then this is going to be measured counterclockwise from the polar axis. And then if it's negative, then it is measured clockwise from the polar axis. Okay? So you're just going in the opposite direction there. Any questions? let's try an example out. So we're going to plot each point, and I got 3 of them. Those are the 3 points I'm going to plot in the polar coordinate grid. Bless you. Okay, now I'm going to redraw that grid. Now here's the deal. I'm going to be very clear on something. You'll see this in textbooks, and I mean, and people do this in general. Do you have to draw a full coordinate grid, or can you just draw the angles you need for that? You can. You can just draw the angles that you need. That's no big deal. Just for the sake of teaching this, I'm going to redraw this so you can see me plotting without having to worry about where I'm at, without drawing like the whole thing. So I'm going to redraw the whole thing over there. But again, when you guys practice this, if you just want to just look at the angles you need for plotting it and just jot that down on your grid, that's no big deal. So here I go. Okay, so there's 5. Too bad there. Okay, so there it is. Okay, I will tell you, if you look up polar grid paper online, you might see them do this, or they might do every 15 degrees. So you might see like additional lines here. But I think the standard is like every 15 degrees, but we don't have to go to that extreme. I think using our unit circle values, that's good enough for me. Okay, I think we're okay. So let's go ahead and start plotting these points. And I'm gonna use colors. If you want, you can just put like point A, point B, if you wanna write that instead. That's no big deal. In fact, I'll tell you what, I'll even put that underneath it. I'll color in, actually do it this way. Okay, so point A, where's it gonna be located? So the angle's 45 degrees, so we're going in this direction, and the radius is 2, so we're gonna count out 2 from the circle, from the pole. So 1, 2, there it is. So there's point A for me. Simple enough. All right. Pink, we'll do pink. All right, so this will be point B for me. Okay, so -5 and 135. So what I do is I go after the angle first before I do the radius. So the angle's 135, so I'm over here, and 5 would be right there. But because it's negative, I'm going in the opposite direction. So I'll be over here. So this is where point B is going to be located. Okay. So far, so good. And the last one, now I have a negative angle and a negative radius. So there's 2 things I got to consider here. I'm going to use green for this guy. So -30 means I'm going clockwise. So I'm down here. And if it was a normal 3, let's see, normal 3 would be here. But because it's negative, I'm going to go to the complete opposite. So it's going to be here. So there is point C. Okay? So a good strategy is take care of the angle first, and then consider the radius. Are you going to stay in that spot, or are you going to go completely to the other side of it? Okay. Any questions? And by the way, I'm not going to do yeah.
Are we going to draw a graph for each of these on the paper?
You can just draw one big one and put them all on there. That's fine.
We're not
All right, but anyway, this, I'll put here, so this is the same process for radians. I'm not gonna draw a full like graph and do an example with radians, but this is all radians, like pi over 6, pi over 4. It's the same process, that doesn't change. All right, let's do some conversions. Now I want to make a note here. So there are an infinite number of ordered pairs that can represent a point in the plane. Okay? So let me give you an example. So if you remember, so just recall that our trig functions are periodic. Okay, so for example, if we have sine of pi over 6, that is the same as sine of 13 pi over 6. Okay, because we just add 2 pi to it, right? And we get the same value. Add 2 pi to it and keep going. I can do the same thing with polar coordinates, okay? So for instance, I can get to this spot again by changing the radius and changing the angle. I can get back to that spot, okay? So that's what we're gonna do in this section here, is I'm gonna give you a coordinate and can we find equivalent coordinates that get me to the same position. So I'll put here the same can be said with polar coordinates. So let's try an example out. We are given 2 and pi over 3 in polar coordinates. We want to find 2 other polar coordinates. Okay. Oh, 2 other polar coordinates representation. There we go. Okay. And we're going to do 2 things. Find another one where the radius is positive, and find another representation with the radius being negative. Okay? That's what we're going to do. I'm going to draw just a little, I'm not going to draw the full grid out, but I'm going to draw a little picture underneath it to kind of explain how we're going to find it. So again, what I want to do is this, kind of like with the trig functions. Like, where do we see sine pi over 6 be the same value? We see at 13 pi over 6. We add 2 pi to it. Okay? So we have 2 and then pi over 3. So let me just, let's say that's here. Without me drawing all the circles and stuff. Okay, so I want to figure out how can I get back to that same position. Okay, do I have another set of polar coordinates that can get me to that? And we can. If I were to take this and add 2 pi to it, do I get back to where I'm at? Yeah, right? Okay, so that's another set of coordinates that can get me to the same position. So let's go ahead and write that down. So 2 pi over 3 plus 2 pi. So we'll add those together, and we get 2, 7 pi over 3. So that point is going to be here as well. Okay. Now, can we get there a different way? We can. So instead of me adding 2 pi this way, could I subtract 2 pi the other way to get there? Absolutely. So the other method, so I'll put or, we'll take our angle and we'll subtract 2 pi. And that'll also get me back to the same position. It's kind of like coterminal angles in a way, if you remember coterminal angles from a while ago. So then this will equal 2 and then negative 5 pi over 3. So those are my 2 answers. Right there. Okay. So all 3 points that I found will always land up right here. Now with a negative, okay, can we do the same thing with a negative radius. Absolutely. Okay, so I'm going to draw another picture. So if you remember from over here, a negative radius just kind of reflected to the other side, right? So what I want to do is this. If I could find this point, okay, and put a negative radius to it, that puts me up here, right? That's what I want to do, okay? Because again, the goal is to come up with coordinates that are at the same position. So if I find that point and put a negative r to it, so in this case -2, that puts me here. I'm back to where I need to be. Okay, so let's go ahead and find those. So I'm out of space. I don't want to squish it in there, so this has got to go. Okay, so we'll do -2, because again, this has to be negative to flip it back over here, okay? And then, to get to that point, if you remember the thing I just erased, to get to this, I could add pi to it, that'll get me to that point. So that's what I'm gonna do, I'm gonna take pi over 3, and add pi to it. So I get -2, this becomes 4 pi over 3. Now visually, let me explain what I just did. So this point, the angle is 4 pi over 3, okay? But because the radius is negative, it puts it back up here. That's what I wanted. So that's equivalent. So these two are the same point. Okay, let's find another one. So let's do one more. So -2, and this time I can go what? This direction. So I'd subtract pi instead, right, to get to that point. And then when a negative r would put me back up here. So it'd be -2, and then we'll do pi over 3 minus pi, which will give me -2 and -2 pi over 3. And again, let me just show visually what I did. So -2 pi over 3 would go in this direction, and then the -2 would bring it back up here. There we go. So they're equivalent. Okay. Now just be careful on something. Okay, could you keep finding other representations? Yeah, there's an infinite number of them. But it's only, when it comes to negative r values, you want odd multiples of pi. Why do I say that? If I subtract a negative pi and subtract another negative pi, I'm up here, right? But the negative radius will put me down there. That's not good, okay? So if I subtract pi, I don't want to subtract 2 pi to find another one, I want to subtract 3 pi for it to work, okay? So when you're doing with an r negative representation, you want to come up with odd multiples of pi you're going to subtract from it, okay? To get back to that same position. But in this case, the problem just wanted 2 representations, so that's all we did. All right? Okay, any questions on that? Cool, let's keep going. Now we're going to do conversions. I was a step ahead. So here we go, converting between rectangulars and polar coordinates. So what I mean is this, can I take a polar coordinate, and instead of it writing that way, can I represent it with an xy point? Okay, that's what I want to do. So instead of me writing this, what is that point in the xy plane? Can we write the equivalent? And we certainly can't do that. It's pretty simple. Okay, so let's do this. Go ahead and draw that picture for me. So again, I want to represent this not with r theta, I want to represent it with an xy point. And I can certainly do that by using a little bit of trig. Use red. Okay, so how am I going to do that? Like this. If that's my point, and I want to know what the y coordinate is and the x coordinate, I'll put y and x here, okay, then looking at that, what I just did to find these values, that's crooked, isn't it? Yeah, that is not a right angle. Whew. That's what you get for writing off to the side. Let's try and make it somewhat accurate here. Okay, that's a little bit better. But by drawing that dotted line, I have a right triangle. And then what I can do, if I know what theta is, I can solve for y and x using sine and cosine. And once I have those values, I know what that is as an xy point. Okay? So let's write that down next to it. So using trig functions, we can transform our polar coordinates to rectangular. Okay? So using this figure, I know cosine of theta is equal to x over r. Sine of theta equals y over r. And again, the goal is I want to know what x and y are. So if I were to solve each one for x and y, over here I get x is r cosine of theta, and over here I get y is equal to r sine of theta. Okay? So if I want to transform that to rectangular coordinates, I just need the radius and do cosine of the angle to find the x coordinate of it, radius and sine of that angle to find the y coordinate. Simple enough. That's how we're going to transform these coordinates. Let's give it a shot. So example, convert the ordered pairs in polar coordinates to rectangular coordinates. I'm going to abbreviate rectangular. I'm getting tired of writing that now. I'm going to try and abbreviate that as well. So I got two little examples with it. We'll do 12, 5 pi over 3. And the other one we'll do -2 and negative pi over 6. All right. Now, cool way we can check our work to see if we're on the right track. Okay? You don't have to do this every time, but 12 and 5 pi over 3. Okay, let's think about that visually for a moment. 5 pi over 3 is in what quadrant? 1, 2, 3, or 4? 4. Yep, it's fourth quadrant. Okay, so it's over here. So the x value is what? Positive in that quadrant, and the y value is negative. So when we do this, if my answer doesn't match that pattern, then it's something wrong, right? So again, just kind of a cool way to check your answer. All right, let's find them. So x is equal to r cosine of theta. Y is equal to r sine of theta. And all we're going to do is plug these values in. I'll label it underneath it. So this is r, and that's theta. So we're going to substitute and then simplify. So here we go. We get 12 times cosine of 5 pi over 3. And then for the y value, we get 12 times sine of 5 pi over 3. So we get 12 cosine, 5 pi over 3 for cosine's a half. Sorry. Don't need the cosine part. That's what it is. Okay, over here we get 12 times negative square root of 3 over 2. So knowing the unit circle stuff, pretty critical in this spot. So x is just going to be 6. Over here, I can see that 12 and 2 reduces to 6 as well. So we get -6 square root of 3. So let's check our work. Is x positive, y negative in that quadrant? Yep, so we must be doing something right here. So my final solution is just 6 comma negative 6 square root of 3. So that's where that point is, which is also the equivalent of 12 pi over 3. Both of those will get you to the same location. Let's repeat it over here. Okay. So first, let's just find a quadrant. So negative pi over 6 means I'm coming down here, right? This is negative pi over 6. But the negative radius is going to flip me over here. So this is in quadrant 2. So in quadrant 2, my y value is positive, my x is negative. So I want to keep that in mind. So when I get my answer, I can see, did I do it correctly? So let's go ahead and start using the formulas. So we get negative 2 cosine of negative pi over 6. And we get negative 2 sine of negative pi over 6. Okay. So what's this give me? So I get negative 2 times, so this would be square root of 3 over 2. On this side, we get negative 2 times negative a half. So the x coordinate, notice that the 2's are going to reduce out. I just get negative square root of 3. And then multiply these together, negative is positive, and it just becomes a 1. So then we check our work. So x is negative, yep. Y is positive, yep. So we did well. Did very good with it. So my answer is a point, so make sure you write it as a point. So negative square root of 3 and 1. Okay? If they want a decimal, you can plug it in for a decimal. That's no big deal. All right. Questions on converting? So we gotta go backwards now. Can we go from a rectangular to a polar? Okay, so let's do that next. To convert back to polar coordinates, we need r, which we can find by Pythagorean theorem. And theta, which we can find by tangent. Okay? So if you look at that picture that I drew right here in the middle board, okay, going backwards, if I know what x and y are, well then I can use Pythagorean theorem to find r. Perfect, that's easy. And to find the angle, I can use tangent because the inverse of tangent will give me that angle. That's all I'm going to do. Okay, so I didn't want to have to redraw the picture again, but using that picture, that's where I'm getting the information from. So let's try an example with it. We're going to convert negative 2 from rectangular to polar coordinates. And here's what we're going to do, because we talked about there's 2 ways of getting to, well, more than 2 ways, but you can write equivalent polar coordinate expressions depending on, how you're going to add pi, subtract pi, or 2 pi, depending on if r is positive or negative. So with this one, we're going to give just 2 representations. One with a positive radius, and then one with a negative radius. So we're going to give an answer, but 2 answers, okay? One that has a positive r value, one with a negative, okay? So what I'm going to do is just draw a picture. It's nice to have a picture. So negative 2 is right there. I'll just put it up at the top. So there's my 90-degree angle. 2, this is -2, and that's r. So we're just drawing a nice little triangle just to see what this looks like. So I need to find r. Doesn't matter if you find it first or last, but I need r. So let's go ahead and do that first. So r squared is equal to, it'd be 2 squared plus -2 squared. I mean, honestly, just 2 squared, because that negative's going to cancel out anyway. So r squared equals the square root. So this would be 4 plus 4, which is 8. And then I will reduce that, so that does reduce to 2 square roots of 2. So r is done. Now I got to figure out the angle. So this guy right here. Okay, so what is this angle going to be? So we're going to use inverse of tangent to find it. Okay? So we're going to have tangent of theta is equal to be 2 over -2, because remember, tangent's y over x. So that just gives me -1. Okay? And here's the deal. So theta is 1 in general at pi over 4. We know that. Okay? But look at what quadrant we're in. We're in quadrant 2. So what's a pi over 4 equivalent in quadrant 2? So it'd be 3 pi over 4. Okay? So our theta is 3 pi over 4. And I'll put it in here because we are in quadrant 2. So we want to be sure, like when you're doing this, it does help to have a picture. That way you can tell, you know, it's not just pi over 4. One, it's negative, so we know we have to pick a quadrant where tangent's negative. But specifically, we're picking a 3 pi over 4, not 7 pi over 4, because we're in quadrant 2. All right. So one possibility is what I just came up with here. Okay, so let's just put answers. So the first one is just what we came up with. Okay, there's all my answers. Now, another answer. So that's when r is greater than 0. So when it's positive. So I'll put here underneath, that's what that answer represents. Now we want an answer when r is negative. Okay, so remember what r does when it's negative. It flips it to the other side. So what I want, I'll draw it on here, is I want to find this point. So when I have the r that's negative, it puts me up to here. So I got to figure out what is that angle. Okay? Well, we can figure out that angle pretty quickly. We know it's going to be the same angle as up here, which is a pi over 4 equivalent. So to go in that direction, you just do negative pi over 4, right? So for my other solution, it'd be this. Let me just put underneath there, this is the negative. Okay? So again, if I go negative pi over 4, that brings it down to this point, and then negative radius puts it right back up to here. So those are my 2 equivalent polar coordinates. Now, there's an infinite number because you keep finding more, but those are the 2 representations we're going to use. All right. We got one final thing to do, but any questions up to this point? Guys are awesome. Okay, so the last thing we're going to do is, can we look at equations in polar rectangular form? Okay, to wrap things up. Quick definition. So a polar equation is an equation described in a polar coordinate system with variables r and theta rather than x and y. Okay. Now, why is that the case? Why is this such a big deal? Let me tell you. Here's a cool looking graph. Okay, let's say I had this graph. Can you imagine that graph with x's and y's in it? it's like a piecewise in a way, right? Be pretty complicated. But if you were to translate that rectangular to polar, here's what the equation is going to look like. So again, if I did a rectangle with x's and y's, it's a lot more complicated. So if I were to translate that to polar, I have something that's easier to work with, okay? So that's the main reason why we do stuff like this. Circles is another one, okay? If you remember equation of a circle, it's x squared y squared equals r squared. Not that that's a complicated one, but I could transform that into a polar coordinate system that's easier to work with, okay? So that's what we're gonna do. We're gonna do some conversions with equations. So another example, write an equivalent equation using polar coordinates. Okay, so there's my equation. We're going to start just something basic just to kind of get our feet wet with it. So there's my equation. We know what that is. That's a line. Okay, but can we represent it in a trig way? That line in a different approach? And we certainly can. And here's the good news. I still have this up here, which is nice. X and y, we can rewrite that in polar coordinates. What does x and y represent? These guys, right? That's what we just talked about when we're, converting this from rectangular to polar. That's our conversions. So let's put this here. So we're going to use the following. X equals r cosine of theta, y equals r sine of theta. I'm going to substitute those in there and then just simplify. And then what's left is a trig equation, a polar equation, that represents the exact same line. Okay? So let's do it. Let's do a little substitution. So this guy right here would be 2 times r cosine of theta plus r sine of theta equals 4. Okay? Now when I say simplify, you want to simplify it fully. Okay, meaning that you have an r on one side and everything else on the other side. Okay? So this becomes 2r cosine of theta plus r sine of theta equals 4. Now because both terms have r, I can factor that out. So I take an r out, I get 2 cosine of theta plus sine of theta equals 4. Which is perfect, because again, I just want one r value equals just blah, whatever's after it. I'll divide both sides by what's in the parentheses. I get r to be 4 divided by 2 cosine of theta plus sine of theta. There we go. Those are my equivalents. Yes?
Would we want to bother converting that to sine 2 theta, or just leave it that way?
Right here?
Or is it 2 sine theta plus cosine theta, not 2 cosine theta plus sine theta? I might.
There's a plus sign there. Because it would be multiplying.
Oh,
Do that
you're right,
conversion.
you're right.
But let me tell you this, if that was, for instance, if that was, it wouldn't be a bad idea to just change it. Because again, that's simplifying it even further.
Okay.
Yeah.
Alright.
All right. Now, we kind of probably made it more complicated. But again, I just want to give you a smaller one to work with, okay? But that's what you do, you substitute and you work with it. Let's do one more and then we'll do one going backwards and we're finished. So let's do same set of instructions. Write an equivalent equation using polar coordinates. And this time we're going to have a circle. And I would, honestly, I'd encourage you, after class, look at Desmos, type these in, see that, hey, they do come out to be the same, which is kind of cool. You'll see the same graph. I'm still going to use the same fact. So I'll put this over here again. So we're going to use this. we go ahead and substitute. Just like that. Now, I will say at the very end, you're going to see how it does simplify pretty nicely. And the equation we get is smaller than this guy, believe it or not. It doesn't look like it because we're going to be squaring some things, but it does come out to be smaller. So we get r squared cosine squared of theta. Now this one, when we expand it, we get the following. Just to save some time, we'll do this. So r squared sine squared of theta minus 4 r sine of theta plus 4 equals 4. So again, I'm just skipping a couple steps, but when you expand it, you get the following terms. Now immediately my eye goes to this because I have a cosine and sine squared. That's a Pythagorean identity. We know that's a 1. So something tells me I probably should be working with this guy next. So speaking of that, let's go ahead and take an r squared out of both of these guys. Okay? So we're going to get r squared, that's an r, cosine squared of theta plus sine squared of theta, and then all this stuff on the outside. So again, the reason why I grouped those is because that's a Pythagorean identity that allows me to simplify it. So that's just a 1. So I get r squared minus 4 r sine of theta. And then what I'm going to do, I'll get rid of this as well. I'll subtract 4 over, that becomes a 0. So I'm doing 2 steps in 1 here. So I'm applying the identity, and I'm taking the 4 out. Okay? Now again, I want to just have one r. So what I'm going to do is factor an r out of this guy. Okay? And then something cool is going to pop up here. So notice, I could use a zero product property to figure out what's going on here. So the first one just says r is 0. The second one, I get r minus 4 sine of theta equals 0. Now, r is 0, that's the pole, okay, on the polar coordinate system. That's the origin, okay? If I solve this for r, I get 4 sine of theta. Now, here's the deal. Which equation is my equation? This is included into here, because if I plug pi in here, I get 0, right? And that's what this is saying. So 0 is included in here, so therefore, all I need is this guy. Okay, I don't have to worry about both of those. So there's my equation. This right here, if you graph it on Desmos, or graphing calculator, and you graph that circle, they're identical. They're exactly the same. Okay? Which, that's really cool. That's a lot of fun to work with. Any questions? So now we're just going to go the other direction. We'll do that, and we'll be done. So now you have another way to write a circle. If I have time, we don't have time, but if there was time, I'd actually have you guys graph both so you can see it yourself. Okay, so now, to finish it, so to convert from polar to rectangular, okay, I'll give you some steps to help. You want to apply one or more of the following relationships. Okay, so the stuff we've been using with x and y. Okay, or Pythagorean theorem, x squared y squared equals r squared, tangent of theta equals y over x. So that's one thing you could do to convert. Use one of those. The second thing you could do is you can multiply both sides by r, and we'll see an example why that can help. The last thing you could do is you could square both sides of the equation. Now you might do all 3 of these in one, you might just do one of them. You don't have to do all of them, but just whatever is needed to convert polar back to rectangular. So when I'm saying that is I'm taking r and theta, I'm changing it back to x and y. Okay? So here we go. So we're gonna write the equivalent equation using rectangular coordinates. I do have one more I'm gonna have to put over here. What do you think? We think we do this in 7 minutes? I think we can. We can do it. I'm sure we can do it, all right? There's small examples, that's why there's 4 of them. So r equals 4. I want to see what does that look like in rectangular with x's and y's in it, okay? So looking at this, if you look at your equivalent relationships, there's really nothing there that's going to help me with this. So let's go to step 2. Let's multiply both sides by r, which actually that's not even good because then you get 4r. Scratch that. Let's square both sides of the equation. So we get r squared equals 16. So I'm using step 3. And we know what r squared is now. R squared is this guy. So I'm going to substitute. So x squared plus y squared equals 16. Hey, no r's, no thetas. We found it. So this is a circle. And the center is 0, 0. The radius is 4. So there's my answer. Okay, so the polar form was 4, but it really represents a circle. And again, like I said, I used the 3rd step to get to this point, and then I used the substitution from here to write it fully in rectangular coordinates. All right, this one has theta, so it means I'm probably using something like this. So I'm going to take tangent to both sides. Okay, so I'm using the first relationship. Now, tangent of theta is y over x, so I'm going to substitute that. And tangent of pi over 4 is 1, so that's nice. And then just multiply both sides by x. I get, oh wait. No, I'm good.
That's not surprising.
Okay, y equals x. So those are equivalent. I would agree, not surprising because we have pi over 4 is at 45.
Yeah.
So that's a diagonal.
45-degree angles.
Yep. Okay, next one. All right, so for this guy, what I'm going to do is change cosecant to 1 over sine. Let's see what that looks like. This is 4 over sine of theta, so it's the equivalence. Now here's what I'm thinking. Look at this. If we have an r sine of theta, that changes to y. So if I multiply both sides by sine, I get r sine of theta equals 4, and then r sine of theta is y, so we get y equals 4. So it's the equivalent. And you'll see, like, for those of you, bless you, if you're going to take like a calc class, you'll see how different forms like this will help. Bless you. All right, last one. Okay, we're going to speed run this. We're going to multiply both sides by r first. Now, the reason why I did that is because r squared is equal to x squared and y squared. That allows me to do that substitution. Okay, so first step, multiply both sides by r. Swap out r squared for x squared plus y squared. Okay, over here, r cosine of theta is just x. This is 4x. Now, here's what I can do. This is screaming circle. So we're going to go back to algebra for a quick second. Okay, so I'm going to subtract 4x over to the other side. And to write it in proper form, standard form with a circle, I'm going to complete the square here. So we take half that and then square it. Add it to the other side. So this would be 0 plus 4. And then last step, we'll factor it. So this is x minus 2 squared plus y squared equals 4. So this is a circle with the center at 2, 0, and the radius is 2. So those guys are the equivalents of each other. Right on the dot, pretty much. Okay, questions? You guys are awesome. Thank you, Frank.